Before starting this practical exercise and the modeling process, let me first introduce the concept of conjugate heat transfer and the basic details of this case involving a power management chip. In this case, we will explore a classic example of a conjugate heat transfer problem where fluid flow and solid heat transfer occur simultaneously. What is conjugate heat transfer? It refers to a physical phenomenon where fluid flow and solid heat transfer occur simultaneously. This is the basis for building such a model. Simply put, it's like this. A fluid at a certain temperature flows over the surface of a solid. There is a temperature difference between the fluid and the solid surface. In this process, as the fluid flows, its temperature will change. There is a heat transfer process occurring between the solid and the fluid. And this heat transfer process is strongly correlated with the flow conditions. In other words, there will be a convective heat transfer coefficient in this process. That's why it's called conjugate heat transfer. In our case here, we have a circuit board, but this circuit board is relatively simple to model because in this course, the main goal is to help you master the modeling process and methods rather than creating a very complex model. The main goal of this course is to help everyone master the entire modeling process and methodology. It is not about building extremely complex models. Since this is a foundational course, the models we build are relatively simple. However, they contain all the essential elements that you would find in any model, starting from problem definition, all the way through to geometry creation, adding boundary conditions, solving, and post-processing. This is a complete process. So, within this framework, we have a PCB board which itself does not generate heat. This is generally consistent with real industrial scenarios. And on this PCB, there is a power management chip, also known as a power management IC. It has a certain amount of heat generation. For this, we set the heat generation to 3 watts. For such a chip, 3 watts is actually considered a normal level. This is because power management chips generally have a high efficiency. Therefore, 3 watts can correspond to a much higher final application power. Then, we place the PCB and the chip in a certain space. You can imagine it as being placed in a box. For example, let's think of it as being placed inside a box. And this box, inside the box, there is air. The air can enter from the bottom and exit from the top, with both the top and bottom surfaces being open. For many real-world engineering problems, there is often a design like this, such as in set-top boxes or industrial control devices, where some holes are made on the surface. However, for simplicity,
we will ignore the details of the holes. For example, we will simply add the condition, where the entire top and bottom are open, allowing airflow to pass through.
Also, we haven't created a corresponding enclosure. For example, the enclosure is usually made by sheet metal stamping. So what we have now is simplified. We have simplified this model. So, what can we obtain from this conjugate heat transfer modeling? We can obtain the temperature distribution. The temperature is expressed in Kelvin, K. We can obtain the temperature distribution. Additionally, we can derive the velocity distribution. This is actually a natural convection problem. The chip heats the surrounding air, causing a change in the air's density. This change in density, under the influence of gravity, the lower density, higher temperature air, will generate buoyancy, which creates a velocity field. We can solve for a velocity field, and essentially this is a convective heat transfer problem. Therefore, we use this model to simulate the process. We use the conjugate heat transfer model to simulate the entire convective heat transfer process, and ultimately, we obtain the velocity and temperature fields. These are the results we get from this model. The key points of the case in this model are as follows. First, the choice of physical structure. For this type of problem, we need to select the solid-fluid heat transfer model. Because it involves both fluid and solid components, such as the chip and the circuit board, we need to select the solid-fluid heat transfer model. Additionally, since the scale is not very large, we temporarily choose the laminar flow model, because in practical engineering problems, you would typically refer to heat transfer textbooks to calculate the Nusselt number and Reynolds number, and then ultimately determine whether the flow is laminar or turbulent. Then we select the corresponding model. At this point, we've simplified that part. If needed, you can refer to our COMSOL 6.1 heat transfer course, which provides a detailed introduction. Then, to link these two physical interfaces, to link these two physical fields, we chose the non-isothermal flow multiphysics node to connect them. This is a key point in selecting our physical interfaces. Additionally, our model definition and the corresponding physical interface functions will be introduced. This includes, for example, how we handle different physical interfaces, how to set the inlet boundary conditions, how to set the outlet boundary conditions, and also other factors such as the heat source from the chip, how to set the convective boundary conditions, and also gravity. That is to say, we need to decide whether we use compressible or incompressible flow, whether to choose a compressible flow or an incompressible flow. We will have some model settings like this. These details will be explained in more detail to everyone.